This is question 4 from Tut 5. So this problem is, you can see the schematic here. Let's read this problem. So assuming an ideal fluid, the shown flow field would occur when the deep open flow of water passes over a submerged semi-cylindrical weir. So this is the semi-cylindrical weir which is submerged by water. The flow is going this way. You can say this is actually the inlet. You can say this is the inlet. So this is the velocity v1. You see it's going this way, so the flow directions. You can see this is actually the open surface, and if you just have a close look, you can see some stenosis area here, actually some sort of bend. So if we say this is the section 1 and this is the section 2, if we consider this center, like if it is the center, so this is the radius 1.2. So from along the center line, the section 2 started from here. So look here, if the local velocities through the section 2 may be expressed by this, so this is actually the velocity profile for this section 2. It is given here. So what we know is this is section 1. Look at this dotted line. This is section 1, this is section 2. Let's say this is A and B, in other words you can say that, and this is a submerged semi-cylindrical weir. We need to calculate the two-dimensional flow rate per meter of the length in the direction into the base. So the distance from here to here, it is given 4.8 meter, and from here to here it is 4.74. So it is says this is y1, this is y2. So what is happening? Initially the flow it is going this way, isn't it? So this is actually the direction. So let's say the flow is going this way. Once it faces this stenosis, this bend area, you see the flow is not going this way, it's coming this way. And if we draw this line, if we draw suppose the flow streamline is here, and then it's flowing this way. So if we draw this line, so from this base to this height, this distance is 4.74 meter. So in other words, we can say that this is actually the the area, because if I say this is the area, so how we can say that? So suppose we have a domain like a rectangular domain. So we know now this is x and this is y. So what is the area? It is x and y, right? So in this case, I'm telling that this 4.8, this is actually the surface area. We need to calculate the flow rate per meter of length. So let's say the length L equals 1. So if we multiply that length with this height, then we will get the surface area. So it should be another meter square. So this is actually the y1, it is meter depth, but this is not the area. But when we will calculate for the per meter of length, so if we multiply this, you can say this is the area. So now instead solving the problem according to the mass conservation principle or the equation of continuity, we can say that the flow rate, the flow must flow at this section, that means the section 1, it should be equal at section 2. And you already know the theorem, the equation of continuity, and the physical meaning of the equation of continuity. I say this is the conservation of mass. So if we use the mass conservation principle for this section 1 and section 2, then we can write so this v1, this is the velocity. So how we will get this? So when we will calculate the flow rate according to the mass conservation principle, you know that if we multiply this velocity, and let's say this is the area. So this formula, this is velocity and the area, and so this is for the section 1. However, the section 2, if we say this distance from here to here, it is y, and in this center, if we take a elementary sections like this, so this is very small section, so we can say that this if it is y, so maybe this distance, this is small elementary section, so this if it is the y, then let's say this is actually dy, very small section, this area is dy, and the velocity here it is v. So when the integration, how we do the integration. So here we will actually use the principle of this integration to calculate the whole the flow rate for this whole domain. So what we will do, we will calculate the flow rate for this small section, and then we will integrate it. So if we write it is this flow rate for this section on, it will be equal to the p, this velocity, and this dy. So we multiply, and then this we'll do some integration. But this is actually the the flow rate for this section, but we need for this whole section. So then we need to put the limit. If you see here, the submerged semi-cylinder, where its radius is if it is the center, so this radius it is 1.2 meter, which means the distance from here to here, this is 1.2. The distance from here to here, it is also 1.2, isn't it? So this radius, this is actually, if you go from this center to any direction, this is 1.2. So this is actually the lower limit for this case, and for the upper limit it is given 4.74. So we'll put this limit, this is 1.2, this is 4.74. And now the velocity profile for section 2, it is given v equal v1 1 plus ryn. So we will substitute that velocity profile, you see 1 plus ryn dy. So we can, from when we are doing this integration, the velocity for the section on this is actually constant. So if we just put this velocity just out of this integration area, then we can write it as v1 and this. So we have the velocity v1 at the left hand side, we have the velocity at the right hand side, so we can eliminate these two terms. So then we have this 4.8, and now look here, we can expand this expression, this velocity profile, like this. Let's say this is 1.2, 4.74, and this 1 and dy. So multiply this, so it will be only dy plus, again the integration, this limit, upper limit, lower limit, upper limit, in the second term 1.2, this is actually the radius, it is this radius, so 1.2 over y and then dy. So now I believe, guys, you already know this formula, the integration. So I believe you know how to do this integration. Integration of dx, this is actually, it is equal x. So this is the formula, so when it is dy, so it should be y and then upper limit, lower limit. And in this section what I did, if you have something like 1 by 2 and yn, so you can write it as, so let's say this is x, this is y, so you can write it as x and yn. So power will be distributed both for this the upper term and the lower term, so it should be 1.2n and y to the power n. So I just wrote 1 to the 1.2, it is constant, so I wrote it just out of the integration, and it is 1, then it will be 1 by yn. So 1 by yn, it's kind of like this, 1 over yn, right? Yeah, so 1 over yn. So if we just it was the 1 over, so if I just write it like this, then according to this simple mathematics, so then we can write this y to the power negative n and dy. And now the thing is, when it is y to the power negative n, so this formula xn, the integration of xn, this is actually xn plus 1, right, over n plus 1. So this is actually the formula we know for for integration. So this formula we have used this formula previously. So here consider this is x to the power n, so this negative 1, let's say this is just n, so that will be n plus 1. It means negative n plus 1, which is eventually 1 minus n, and for this lower part, you see this is 1 minus n as well. So then we put this limit, and now we just substitute this upper limit, lower limit, this. So once we have done this, then we need to just solve this expression. So now if we solve this, then you will see that we will get n equal 1.2. So we solved this and we got this value, it is 1.2. So we got this this constant n equal 1.42. So maybe you can ask me why I calculated this value, and so definitely I will answer this question later. So let's use the Bernoulli principle now along with this a and b. So this is a and b. So along the free surface, if we use the Bernoulli principle, you already know the mathematical formulations. So b1 squared 2g p by rho g and the z. So this is for section A or section 1. This is for section B, or you say section 2. When we are calculating the when we are applying the Bernoulli principle along the free surface, so along the free surface, the pressure for this section A and the pressure for this section B, it will be 0. So that means you can remove these two terms. The pressure is 0 here. The velocity v1 actually we will calculate, and we actually know the velocity profile for v2. If you see the question here, this is actually the velocity profile for section 2. So we know r, okay, we know y for the section 2, but the n, it is unknown, this constant. That's why we calculated this n, because we need to calculate the velocity for section 2. So now let's calculate the v2. So what we need to do is we need to substitute all of the value. So let's have a look. So here this is the velocity profile. We just substituted r, y and n. So we got the velocity v2 is 1.142. So now once we know 1.142, so we know the gravity, right, and we know the velocity. So if we substitute all of those values here, then we will get v1. So see what I did. This is the gravity, and 2, it is 2g, so 2 into 9.8. So we know this, we substituted this v2 and the other values, and we got this is the velocity for section A, and we need to calculate the flow rate. So that means we need to multiply the velocity and the area. So we got it. So that's actually the flow rate. So the main thing is initially we need to calculate the constant n, because in this velocity profile, this constant n, it is unknown. So we did all of these simplifications from here. We used the mass conservation principles to get that value, and once we got this n, then we used the Bernoulli principle, and by using the Bernoulli principle we got the velocity here for section 1, and then we calculated the flow rate. So that's the solutions. So what I will tell you is I believe this is important problem. So I will tell you, okay, try to find out some similar problem from different books and just practice it.